All right, let's dive into one of the most fundamental partnerships in the entire universe. It's this silent, invisible dance, a powerful collaboration that, it literally makes our modern world go round. So think about this for a second. An electric car, a giant wind turbine, and your refrigerator. What could they possibly have in common? On the surface, they seem completely different, right? One moves you around, one catches the wind, and the other just keeps your snacks cold. But believe it or not, they all share this deep, invisible secret. And that secret, it's all about a partnership between two of nature's most basic forces, electricity and magnetism. For centuries, everybody thought they were totally separate things. But then, back in 1820, a physicist named Hans Christian Ørsted stumbled onto something huge. He found a connection. And that one discovery kicked off a revolution that, well, it powers just about everything in our lives today. Okay, so let's break down the first part of this relationship. Think of it like a dance where electricity takes the lead, creating motion from, well, seemingly nothing. It all starts with a simple but totally world-changing idea. Here's the core principle, and it's actually pretty straightforward. If you run an electric current through a wire and you put that wire in a magnetic field, that wire is going to move. Something invisible will actually push it. So electricity creates motion. That's it. It's called the motor effect, and it's the first big step in this whole invisible dance. Okay, great. So the wire gets a push. But which way, right? A random, unpredictable force isn't really useful for much. If you want to actually build something with this effect, you need to be able to predict and control that push. And luckily for us, there's a brilliantly simple trick for doing just that. Say hello to Fleming's left-hand rule. Yeah, it might look a little funny, but trust me, it's incredibly powerful. Just hold up your left hand, like this. Your forefinger, that's the magnetic F field. Your middle finger points in the direction of the current. And what about your thumb? Well, your thumb points in the direction of the resulting force, or the motion. Field, current, force. It's the motor rule, and it is exactly how engineers figure out how to build basically every electric motor out there. And that leads us straight to the first and maybe the biggest application of this whole idea, the electric motor. This is a device that completely reshaped human civilization as we know it. So what's actually inside one of these things? Well, you've got a coil of wire that spins, that's the armature or rotor. It sits inside a magnetic field created by some strong stationary magnets, which we call the stator. Then you have brushes that feed electricity into that spinning coil, but the real magic, the absolute genius of the design, is this little thing called a split ring commutator. This little ring is the absolute key to making the motor spin continuously. See, without it, the coil would just get pushed, flip over once, and then get stuck. Game over. But the split ring commutator is this really clever switch. Every time the coil does a half turn, it reverses the direction of the current. And by doing that, it flips the direction of the magnetic push at just the right moment, so the coil gets another kick in the same direction over and over and over again. All right, so we've seen how electricity can create motion. Pretty cool, right? But here's where it gets even more interesting. This partnership, this whole dance, it's a two-way street. And this leads to the next logical question, right? It's the exact question that obsessed the scientist Michael Faraday back in the 1830s. If you can use electricity to create motion, could you do the reverse? Could you use motion to create electricity? Well, the answer turned out to be a huge, resounding yes. And this is the other half of the dance. It's called electromagnetic induction. Now here's the crucial part, the real key. A magnet just sitting next to a wire does nothing. The magnetic field has to be changing. That means you either have to move the magnet past the wire or you have to move the wire through the magnetic field. It's the motion that makes it all happen. And you guessed it, just like we had a rule for motors, we have one for generators. But this time you use your right hand. So it's Fleming's right-hand rule. Same exact setup, just the other hand for the opposite effect. Your thumb points in the direction of the motion, your forefinger points in the direction of the field, and now your middle finger tells you which way the current is going to flow. And this discovery is, well, it's everything. It's what allows us to do the exact opposite of a motor. It's how we generate pretty much all of the electricity that powers the entire modern world. You can see the beautiful symmetry of it all right here. A motor and a generator, they're basically the same device, just run in reverse. It's all about what you put in and what you get out. Put electricity in and you get motion out. That's a motor. But if you provide the motion in, say by spinning a turbine with wind or water or steam, then you get electricity out, and that's a generator. Yep, they are literally two sides of the same electromagnetic coin. Think about it. The very same principle that makes the fan in your room spin is the one used at the power plant to generate the electricity to make it spin in the first place. It's just perfect. Okay, so there's one more important detail. When a generator spins that coil in a magnetic field, the current it creates isn't like the steady one-way flow you get from a battery. That's direct current, or DC. Instead, it naturally creates a current that flips direction, back and forth, over and over. We call this alternating current, or AC. And as it turns out, that constant back and forth is actually its greatest superpower. So let's bring this all home. Let's see how this incredible invisible dance is the foundation for the entire electrical grid that powers, well, everything. Our homes, our schools, our entire world. This actually led to a famous showdown called the War of the Currents. You had Thomas Edison on one side, pushing for DC, and Nikola Tesla on the other, championing AC. In the end, AC won, and it won for one giant reason. You can change its voltage super easily using a device called a transformer, and that single advantage made it way, way more efficient for sending power over long distances. And here is why that is such a game changer. Trying to send a lot of electric current through a wire is like trying to force a ton of water through a tiny pipe. You lose a huge amount of energy to friction. With electricity, that energy is lost as heat. But with AC, you can use a transformer to step up the voltage to insane levels, like 400,000 volts. By doing that, you can send the exact same amount of power with just a tiny trickle of current, which means almost no energy gets wasted. Then when the power gets near your house, another transformer steps it down to a safe voltage for your wall outlets. And finally, that power gets to your home through three main wires. You've got the live wire, which is the one carrying all the voltage. You've got the neutral wire, which is basically the return path that completes the circuit. And then you have the earth wire. And this one is a super important safety feature. If something goes wrong, it gives the electricity a safe path straight to the ground, which can save you from a nasty electric shock. So there you have it. From the tiny motor in your electric toothbrush all the way up to the massive generators that power our cities, it all comes back to this one elegant, invisible dance between electricity and magnetism. It's a partnership that was only discovered a couple of centuries ago, and yet it has completely reshaped what it means to be human. It really makes you wonder, what new steps are we going to choreograph next?